Hey everybody, Mr. Kowalczyk here. So sorry I couldn't be there today. Here is our lesson for 7.5. So what we have is, in this particular situation, we have a gigantic mantle squid. And the mantle of the squid. This is sea level right here, going across. Let me point with my pencil. So we got sea level here, and then the distance from the person who is abandoned on a raft and just so happened to have a laser measuring device just because they had a ruler and they had a knife and a mirror and buttons and all this other stuff. So what happened was this gigantic mantle squid came up out of the surface to say hello to this person who was kind of just floating around on their raft. And the person thought to themselves, I wonder how tall the mantle of the squid is, which goes from this part to the summit of the animal. All right, so let's go ahead and use some math to figure it out because why not? Random situation. All right, now what happened was this person used their ingenuity to place a mirror that was 4.1 feet. I don't know if you can see that, but it says 4.1 feet away from them on their raft. That they're standing perfectly perpendicular, and therefore it bounced off the mirror. Their light rays bounced off the mirror and up to the gigantic top of the mantle of the squid. Now they use their laser measuring device to determine they're 4.1 feet away, and they're also 12.7 feet away there. Now, what we know is we have similar triangles. Well, how do we know we have similar triangles? We're going to use angle-angle similarity to figure that out. We know we have right angles because the squid, of course, cooperated and came perfectly perpendicular to the surface of the sea. And then the person is standing perfectly perpendicular to the surface of the sea as well, which means that this line here is parallel to this line here. Because we have parallel lines, we also know that our angles are going to match up as well. The angle here, this angle right there, the reflection off of the mirror is also going to be congruent. That's going to match up perfectly because it bounced off the mirror and came back up perfectly. So we have two similar triangles based on angle-angle similarity. Therefore, we can set up our proportion of height of the person to height of the squid equals the distance of the person, or we'll call it lateral distance, right? Because it's the lateral distance this way to the mirror over the lateral distance of the squid. That's my idea. Now I'm going to plug stuff in. I've got 5.5 over height of the squid, which is my unknown. And that's going to equal the lateral distance, which is going to be 4.1 over 12.7. We cross multiply and do 5.5 times 12.7, and that's going to equal 4.1 times the height of the squid. All right, calculator. 5.5 times 12.7. That's going to give me 60.85, equaling 4.1 height of the squid divided by 4.1. Height of the squid equals 17.03 feet. And that's only part of the squid. That would be terrifying. All right, that was a good warm up. Let's move on. So unit 7, ratio, proportion, similarity. This is our last lesson that we're going to do for this particular chapter. Proving triangles similar with side angle side similarity and side 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 similarity. And these triangles are happy. They're in love. They are so similar. This is 21, and this is 15. And then we have 7, and then we have 5. We know that the scale factor is what? 3 or 1/3. Notice there's a congruency mark here and a congruency mark there. That's going to be side angle side similarity. Okay, let's go ahead and jump in here. Our first two theorems for today. Hopefully you took notes on these already. So we got theorem 7.1, side angle side similarity theorem, and theorem 7.2, side 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 similarity theorem. Let's look at this one first. If two pairs of sides are proportional and the included angles are congruent, right? Angles have to be congruent, and only two pairs of sides are proportional, the triangles are similar. So what that means is that AD is proportional to DF and BC is proportional to EF. So we have AC being proportional to DF. So that matches up here. And BC is proportional to EF. And we have an included angle, right, between those two sides that are proportional. Then the two triangles are going to be similar to each other. Just like the triangles in the cartoon, right? That was this one here. So we had side, and then the included angle, and the side. Now the two sides are proportional to each other, so we have 7, congruent, and 5. So we've got those being congruent to each other, angles congruent, and the sides that are on the outside of the angle being proportional. Next one is going to be side similarity theorem. This one says is that all 3 pairs of sides are proportional, then the triangles are similar. Now, this differs from side with congruency because obviously with congruency, they weren't in proportion to each other. They were just equal to each other. So we have to make sure that we're dealing with congruency or similarity and be sure to state them appropriately. So, pardon me, shortcut for this one would be side, angle, side, similarity. Shortcut for this one would be side, similarity. Now the question is, are these triangles similar? If yes, state what postulate or theorem allowed you to do so. To conclude so, I got an extra do in there. So we have our 3 postulates and theorems. We have angle, angle, similarity. That's a postulate. And then we have side, angle, side, similarity, and side, similarity. And those are our theorems. So that's what we have to choose from in these situations here. So let me break out the colors because I told you several times to redraw and it's going to make a difference. Now, at this point, if you want to cross or pause the video and try to figure it out on yourself by yourselves, I highly recommend doing that. If you're not up for that and you feel like you would like to watch me teach this and go through all of these, that's cool too. All right, so we have our green triangle and we also have our purple triangle. So I'm going to redraw so I know what's proportional. So they're oriented the same way. Okay, so I've got 3, 5, and 6. And then I also have 6, 10, and then 6 plus 6 is going to give me 12. So now what I need to do is say I've got 6, and so I'm going to do big to little. So I have 6, 10, and 12. And those correspond to 3, 5, and 6. And that works out. 6/3 is 2, 10/5 is 2, and 12/6 is 2. So that equals 2. Therefore, these 2 triangles are similar. Yes, by side, similarity theorem. Yay. Okay. Now, we've got our 2 triangles here for our second example. We've got green and we have purple. All right, so now what I'm seeing is that my green triangle and my purple triangle both have a congruent vertical angle. Just got to point that out. That's awesome. Now, the next thing that I see here is that these 2 triangles have 2 tick marks here and 1 tick mark here, 1 and 1 and 2 and 2. So I look at this, and logically what this tells me is that M and N are midpoints because they create 2 congruent pieces on either side of the segment. And I also notice that this side is twice as long as this side here. And this side is twice as long as this side. Sorry, this side is twice as long as this side here. So what that tells me is that GJ is 2 tick marks to 2 tick marks, JL as HJ is 2 MK. Therefore, the two sides are in proportion to each other, and the angles are congruent, right? Angle KJL is congruent to angle GJH. Therefore, triangle, and I'm going to make my similarity statement here. I can because I have labeled points. I couldn't over here because I didn't have any labels. Triangle GJH is similar to, now I got to be careful here. I started with G and I went across the side that had two tick marks to my angle. So that's going to be this side here. Triangle L across the side with two tick marks to the J and then out to the K by side angle side similarity. All right, let's take a look at our third one. I have two triangles. Right away, I noticed that shared angle D, right? We've been dealing with that for the last couple days. And I've got sides being proportional to each other. Are they? Well, let's check it out. We've got our smaller triangle in green and our bigger triangle in purple. Okay. So what that tells me is that 12 here corresponds to 12 plus 5, which is 17. And does that equal 6 on the green to 3? Nope. 9. 6 plus 3. 6 plus 3 on the purple. Well, I know that 6/9 reduces to 2/3. 12/17 does not reduce because 17 is prime. And I know that that's not going to work out. These things are not equal to each other. Therefore, the triangles are not similar. Even though this angle was congruent, the sides are not in proportion to each other. So those triangles are not similar to each other. Awesome. All right, let's keep going. What's your favorite part of geometry? Okay. All right. So now we have two proofs that we're going to do. Yeah, we got two more proofs that we're going to do. All right. So we've got AB is to SR as BC is to RA as CA is to AS. So they're in proportion to each other. And what we're trying to do is we're trying to prove that BC is parallel to AR. Okay. So this is a given. All right. Now, of course, you are absolutely welcome to pause the video and try this on your own. All right. So what I'm trying to do is I know that all these sides are in proportion, and I'm trying to prove that BC, this one here, is parallel to this one here. So how can I prove parallel lines? Well, probably with congruent angles. I wonder, I've got maybe, let me do this in pencil because I'm not sure yet. If this angle here is congruent to this angle here, then AC would be my transversal and these would be my alternate interior angles. If I could prove that, then I could prove that these two lines were congruent to each other. So first off, let's see if we can prove that these three triangles are similar to each other. So I know that where are we here? AB is to SR. AB is to SR as BC is to RA, as CA is to AS. CA is to AS. Cool. So what that tells me is that all three sides are congruent, or excuse me, are in proportion to each other, and therefore the two triangles are going to be similar. So right away, I can say triangle, and let's go ahead and do this carefully. ASR is similar to triangle. Now I got to be careful about this. I have AS corresponding to what? AS corresponds to CA. So that means if I start here at A and it goes this way, then I have to start here at C and go this way. Triangle C, A, and B is my last point, so I have to wind up there. What's the reason for that? Side, 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 similarity theorem. Okay. Now, because the two triangles are similar, now I can say the two angles are going to be congruent because I know they correspond to each other, because A is my first letter here in this statement. It corresponds to C, which is my first letter there. So now I can say angle RAS is congruent to angle ACB. I have to use 3 letters here. Then this one I could just use 1 because there's only 1 angle there, but I chose to use 3. What's the reason for that? The definition of similar triangles, which tells us that all 3 sides are in proportion and all 3 corresponding angles are congruent to each other. Now we're good to go. We're done. For BC is parallel to AR because that congruent alternate interior angles give us parallel lines. Yay! All right, hope that made sense. Draw a diagram, state your given, prove, and then prove it. If you tried this yesterday on the quiz, then something similar to this, then you kind of know where we're going. If 2 quadrilaterals are similar, so that is our given. Then the lengths of corresponding diagonals are in the same ratio as the lengths of the corresponding sides. Lengths of the corresponding diagonals are in the same ratio as the lengths of the corresponding sides. That's going to be our proof. Typically, your hypothesis is your given, and your conclusion is going to be your proof. All right, so let's draw a diagram. We got 2 quadrilaterals that are similar to each other. A, B, C, D, with diagonals. And we'll draw a smaller version of that. W, X, Y, Z, with diagonals also. All right, so now our proof. Lengths of the corresponding diagonals are in the same ratio as lengths of the corresponding sides. So what that means is that, so we got our diagram. I'm getting ahead of myself here. I have to have my givens, which is A, B, C, D is similar to W, X, Y, Z. And what are we trying to prove? We're trying to prove that the sides, the diagonals, so we have BD is to XZ as AC is to WY as all of the sides are in proportion to each other. AB is to WX as XY is to, oops, BC, sorry, that should have been BC, is to XY as CD is to YZ as DA is to ZW. So we're trying to prove that they're all in the same ratio to each other. Cool. All right, let's get started. 1. A, B, C, D is similar to W, X, Y, Z. That's my given. All right, now for 2. What I'm going to do here is I'm going to try to prove that these triangles are similar to each other. And just like those, I'm going to also try to prove the other triangles are similar to each other. And that's going to be pretty easy because I can use side angle side similarity with the triangles. So first thing I need to do is I need to start with my angles. So what I want to do is I want to say this angle here, this whole angle here is congruent to this whole angle here. And then I'm going to say that this side is in proportion to this side, and this side is in proportion to this side. We already know all of those things are true because we know that these quadrilaterals are similar. So I can say angle BCD is congruent to angle XYZ. And that's going to allow me to prove these 2 triangles congruent. Let me use some colors here because I'm starting to get. All right, first thing I'm going to do is I'm going to prove these triangles similar to each other. I think I said congruent before. Okay, so those two triangles, and then I know that BC is similar to XY. It's in proportion to, and then we know that CD is in proportion to YZ. Okay, and that's going to be the definition of similar polygons. We also know, let's look at another set of triangles. So that's going to encompass these two diagonals, DB and ZX. So we also need to look at these triangles here for the other diagonal to be in proportion as well. Okay, this is a hard proof. Stay with me on this. So then what I'm going to do is I'm going to say the same thing, but I'm going to use angle ABC and angle WXY. Angle ABC is congruent to angle WXY. And I'm also going to say AB is similar to WX as BC is similar to XY. And all of that falls under the definition of similar polygons. So now we can say the two triangles are congruent, or similar. I did it again. Triangle DBC is similar to triangle ZXY, and triangle ABC is similar to triangle WXY. And that is because of side angle side similarity postulate. Nope, theorem. 4. Now I know, because those triangles are similar, that the diagonals are also in similar ratios. So that tells me that BD is to XZ as the other sides of the pink triangles are. BC is to XY as DC is to ZY. So that's one side of the pink triangle. And then I can also notice that side BC is in the yellow triangle as well. So therefore, AC, the diagonal there, and WY are also in proportion to each other. AC is to WY. And that's my definition, again, of similar polygons. So here I've shown that my diagonals, this is a diagonal, this is a diagonal, and these two are sides. So the diagonals are in the same proportion as the sides of the lengths of the corresponding sides in the triangles. That's a good one. We haven't done one like that before. Make sure you know how to do this one for sure. Okay, that you can follow along and understand what's going on. Okay, folks, that's it. Please work on your homework, and I will see you on Monday for the test review.